Greetings everyone, Professor Simon here, ready to upgrade your efficiency at derivatives. That's what we're going to jump into today. We're going to talk about how to take a derivative without having to write out the pesky limit definition every single time, right? As you can remember from the previous lectures we've been doing, whenever we take a derivative, I have to write either limit as h approaches 0 of f of x plus h minus f of x all over h, difference quotient version, right? Or limit as x approaches a of f of x minus f of a all over x minus a, right? We have the alternate version of the definition of derivative. And those can get tedious. And quite frankly, when you want to take the derivative of something massive and complicated, those limits can be a little bit interesting to try and resolve. So what we have are usually by a lot of students and other people the shortcut rules, right? Really what these are our derivative laws that work 99% of the time. And when I say that, what I mean is you just got to be careful of all of those funky derivative points that you already know should have difficulties, like cusps and discontinuities and things like that, okay? So for the most part, the laws we can just use anywhere, and they allow us really to find the derivative of any function you can imagine, any combination of functions. Over the next few sections, we'll talk about several of these laws, but for this one, let's start with the basic ones, okay? This first one should be a little bit of common sense because remember, derivative measures a change in something, right? So remember, d over dx is the way that I symbolize that I'm going to take the derivative of something. This is the way that I can symbolize doing a derivative action, okay? Or what's one of the ways. So if I take a derivative with respect to x, in other words, I'm letting x be my variable, my independent, of something that is constant, right? Something that can still be considered a function, but it doesn't actually involve x at all, right? So it's constant in terms of x. Then the answer is going to be 0. The derivative measures a change in something, and if there's no x to change in it, right, because x is our independent variable, then there's not going to be any measurable change, right? But we can also prove it mathematically. If I let a function equal some constant, right, it doesn't really matter what this is, as long as it's not something that depends on x, right? This is just some value over here other than anything that relies on x. So then if I take the derivative, f of x plus h and f of x would both be c, because plugging in a different x doesn't give a different value. It's always equal to c, right? So c minus c gives me 0 in the numerator. 0 divided by h is still 0 for every value. The limit as h goes to 0 of 0 is 0, okay? It's a bit of overkill, but it's a very handy rule to get through our derivatives quicker for those things that don't have x in them, okay? Next, probably the most used basic derivative rule is the ability to take the derivative of some variable x raised to some number power, okay? Now, I do need to say this. This rule works for any value of n, okay? It could be x to the 5th, it could be x to the 100th, it could also be x to the negative 5th or negative 100th, it could be x to the 1/2, it could be x to the 3.141592, right, the pi power. As long as n is just some number, n cannot be a variable, n is some number and it's in the power, and the variable is the base, x is the base, right? So this rule is quite powerful, all right? It works for any exponent on a variable x. However, because we're doing a rigorous course here, I can actually only prove 1/3 of it for you at this time, okay? As we build up more of our differentiation laws, I will be able to incorporate the more intricate versions of this, and we will build in the next 2 lectures. You'll see it'll build up. Okay, for now the only piece that we're going to use is the part where n is a positive integer, right? That's what this z, the double line z, remember, is the set of all integers, which is all of the non-decimal numbers, positive n, negative n, 0. Okay, and I've picked the positive integers only. Don't forget, the positive integers also does not include 0, but really you're not interested in the case where n is 0, because anything to the 0 is 1, and that's this rule. The derivative of 1 would be the value 0. So you're not really interested in n equals 0 anyway. Okay, so if n is a positive integer, then that's going to basically be anything polynomial. X to the 1, x to the 2, x to the 3, x to the 4, right? Anything polynomial, single term like that, is going to fall under this rule and have this derivative law behind it, that you can just quickly get the derivative without having to do the limit. So of course, to prove it, we're going to do the limit generically, right? I'm going to use the alternate version here just because the math falls out faster. Okay, so right here, if I let g of x be some x to the n power, right? N is just some integer, positive integer. Then using the alternate form to get the derivative of g at some value of a, I'm going to take the limit as x approaches a of x to the n, right, the function, minus a to the n, which is just g of a, right, over x minus a. However, x to the n minus a to the n I can factor like this. Now before I go in too deep and just say, ooh, look, here it is, let's talk about this for a second. Look at the bottom right here. Just focus right here at the bottom. Okay, don't worry about any of this yet. You know this one already. X squared minus a squared. That's a difference of squares. Okay, x minus a, x plus a. What you may not have seen too much of is the fact that you can actually factor the difference of any 2 powers that are the same. Okay, so this is difference of 2 squares. You can also factor difference of 2 cubes, which you may have seen before. There are formulas for that come out in algebra all the time. But actually, you can do any exponent with this. You can do difference of 4th powers, difference of 5th powers, difference of 6th powers. Here's an example, difference of 7th powers. Okay? Follow the pattern with me before we get there, though. Notice I always start with x minus a on each of these, right? That's how you can always start with a difference of powers here, right? The other piece just needs to be a summation of all of the possible combinations that add up to the missing amount of powers. Okay, so let's say all that again in another way. If I have squares, right, I take one of the powers away by doing the x minus a. So the only thing that's left is 1 power, because it's a total of 2. Okay, so that's just an x and an a. That's the only way you can get a single power of something, 1x or 1a. Okay? But here with a cube, if I take a power out of it, that means there's 2 powers left. So I'm going to do the different combinations of having a degree 2 term. Right? I could have 2 x's, I could have 1x and 1a, or I could have 2 a's, you see? And then if I FOIL this back out, you see that this is what you'll get. So if x to the 7th minus a to the 7th, if I'm going to factor that, x minus a takes one of the powers. The rest of everything in the next term is going to be a sum of all of the things that can be a degree 6 term. So that could be 6 x's, that could be 5 x's and 1a, that could be 4 x's and 2 a's, so on and so on and so on, all the way down till I get 6 a's, right? I just keep going through all of the different possible combinations. And really all I'm doing is I'm letting the x powers count down while the a powers count up. That should sound familiar to you, remember? Because we talked about the binomial theorem just briefly and using Pascal's triangle. The only difference here is I don't need to put coefficients. They're all just one of each, right? To do this kind of factoring, that's the scheme for doing a difference of powers like this, okay? So you can do this with any power. hence what I'm doing here. So I have x to the n minus a to the n, right? So I factor in x minus a out. And then all of the terms that are left in the other piece are supposed to be 1 power less than the one you started with. So I started with n power. So notice this is x to the n minus 1, right? But if I keep counting down, that would be x to the n minus 2, x to the n minus 3, n minus 4, da 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 da, until I get to the last term, which has no x's, x to the 0 basically, right? And then vice versa for the a's, I count up. I have no a's, 1a, 2 a's, all the way up until a gets to 1 less than the original power, n minus 1 in this case, okay? Now, how many of those terms are you going to always get? Well, let's count, right? For difference of squares, the second thing has 2 terms. For a difference of cubes, there's 3 terms. Difference of 7th powers, count them, 1, 2, 3, 4, 5, 6, 7 terms, right? Okay, but think about it. You're actually already counting that every time you count the powers down, right? Because I'm going to count from n minus 1 all the way down to x to the 0. So basically I'm counting n minus 1 to 0, right? Which is going to be an n number of terms. This second set of parentheses is always going to have n number of terms because of the way that you have to count all of the powers in between. Okay, it's basically enumerating itself from n minus 1 to 0, or vice versa, from 0, a to the 0, all the way up to a to the n minus 1. Either way you count it, it's still n terms. Okay? So notice the x minus a multiplied here, x minus a divided here, those are going to eliminate, right? They're going to reduce, leaving me with just these terms. Just the thing that's in the second parentheses here, right? And then the limit as x approaches a, basically everything is continuous here now. So I know that means I can just plug in my a for all of the x's. Okay? So that's going to be a to the n minus 1, first term. A to the n minus 2, then times a again, just gives me a to the n minus 1 again. Right? Basically, you'll notice that all I'm going to have is some a's and some more a's. But each term had to be degree the same, right? They're all degree n minus 1. So if both of these, if I plug in a for x and they're both a's, I'm just going to mash them together, and there's going to be n minus 1 of them every time, right? A to the n minus 1, a to the n minus 1, bam, 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 all the way to the very last one, which is already a to the n minus 1. But remember, we just said, how many terms were there here? There were n of them, right? So there will be n of these things, and they're all the same thing, a to the n minus 1. Combine them all up, and you have n times a to the n minus 1. And really, a was just representative of where I wanted to take the derivative at. So a could be any number anywhere on the function. Basically, what we're saying is a could have just been x, right? From here. So the derivative of a singular monomial from a polynomial like this with integer positive powers, right, is going to be n times x to the n minus 1. Okay? So we're going to start with that stage for now, and then later on when we get more of the structural laws, I'll be able to build 2 more stages to this one, and it'll become a very, very useful, extremely useful law. Okay? This one. Some basic structural rules. These two come out to be what we like to refer to the derivative being a linear operator. Something that's a linear operator is something that works well with addition and subtraction and distributive property of multiplication. That's basically what we call a linear operator, something that works well with those things. Okay? So here's one of the things that comes with that. If I know the derivative of some function f of x, and I happen to stumble across a version of that function where it's just an extra number multiplied in front of it, okay? So in other words, if I know how to take the derivative of x to the third, right, that would be 3x to the 2, right? Then let's say I had 5 times x to the third. Well, this rule is basically saying that I can just take the multiplied number and just bring it along for the ride. In other words, make him wait a minute. Take the derivative of the actual function part that you know, just the f prime part, you see, and then multiply that number times that result. And all this is basically just factoring a GCF, because if I have some constant times a function inside of my difference quotient, I can factor that k out front, and then the limit of just this piece is still the same derivative that you already knew, and the k is just factored out. Okay, so if you have a multiplied number, just a constant, okay, that can't be another function, that's different. But if you have a multiplied number or something that doesn't depend on x, then it can just pull out and follow along. Okay? Also, the other part of being a linear operator is if you have two objects that you recognize separately, but they're added or subtracted, right? There's some sort of sum going on there, then you can act your action on each individual piece and bring the addition or subtraction just along in between them like they were before. Okay? And again, this is just basically our rules of addition and subtraction, just like this one was GCF and distributive property. This is our associative and commutative properties of addition and subtraction, right? If I have the original function in a difference quotient, I would have to put in x plus h into both, minus the original function, right? And you'll notice I'm using the addition part because subtraction is really just addition of a negative value. So it's the same thing. Okay? So this is the original setup, but notice all I really need to do is distribute this negative to both of these pieces and then use the commutative property to rewrite the numerator as f of x plus h minus f of x and g of x plus h minus g of x. And they're both already over h, I just distribute it out. And then notice that's each of the derivatives separately, but added together. Okay? So the derivative of a sum is equal to the sum of the derivatives. Okay? Unfortunately, this does not work for multiplication of two functions. That's next lecture when we talk about product rule. Okay? So don't get those two confused. If I have addition or subtraction between two functions, then I can work them separately in a derivative. Okay? So these four rules right here, you need to know these rules. Okay? And of course, as you practice them, they'll stick to you. All right? Let's get some examples. Let's get some examples of these first few basic rules. Okay, let's start here. Let's say I've defined my function just y equals pi. And it's asking for the derivative with respect to x, right? dy over dx. That means x is my variable. Pi is typically not a variable, right? Pi is typically a constant, right? We tend not to mess with that letter too much. And it doesn't depend on x. So what is the derivative of a constant? That would be 0. Right? Okay, first rule. Next, what if I have a function z is equal to x to the 17th power? Now here's an example of something that you would really not like to do with the limit definition of derivatives, because you would have to expand out an x to the 17th power, and that has lots of terms, right? To have to do this one with the definition would just be cruel and unusual punishment to a student, right? However, we have a nice, beautiful power rule, is what that one was called, right? X to some number power, as long as it's a positive whole number, is what we've done so far. So the derivative is 17 times x to the 16, right? I just dropped the n minus 1 is the new power, right? So there's my derivative of x to the 17th. That's simple, just boom. Okay, here, Same thing with a power rule, right? I have the t squared is my function. H is a function of t. T squared is the actual function part of it. And negative 16 is a multiplied number. So that negative 16, remember, as a multiplied number, I'll just carry over and multiply times the derivative of the functional part. So in this case, notice, be careful now, it says dt in the bottom, right? And t is the variable I'm taking the derivative of. If this said dx, then the derivative of this would be 0, because t doesn't depend on x in this case, right? But look, it says dh dt, and t is our actual variable. So we're good to do derivative. The negative 16 is going to follow, and the derivative of t squared is 2t, right? Because I'll drop the 2, and 2 minus 1 is 1, right? So it's t to the 1 technically. But we can simplify this. It's just negative 16 times 2. That's negative 32t. Okay? Now, the last rule that we talked about was what happens when you are combining two separate functions with addition and subtraction, right? Well, we said that the derivative of the sum is the sum of the derivatives. So I'm just going to do the derivative of the x cubed, and I'm going to do the derivative of the x separately, and I'm going to keep the subtraction between them. Okay? Don't make the mistake of putting an equal sign here. I see that a lot. Don't do that. This is the function f. His derivative would be f prime, or you could also put df over dx. That would work too. Okay? So f prime, I'm going to do the derivative of just this part right here. 3x squared. I drop the 3. 3 minus 1 is 2. The minus 4 is along for the ride. It's a multiplied constant. Times derivative of x to the 1. So I drop the 1 and then x to the 0. Because 1 minus 1 is 0. Okay? Now, just a little side note for a moment. You should know that the slope of a line is the number in front of the x. And this is a linear portion right here, negative 4x. So the derivative of that had better be negative 4. And it is, right? There's the negative 4 times 1, and anything to the 0 power is 1. Save yourself a little time on the linear portions. If it's x to the 1, the derivative is the coefficient. Okay? Let's simplify here. I'm getting that the derivative is 3x squared minus 4, right? Because it's basically 4 times 1 times 1. Okay? Now you should recognize this. Previous lecture, we actually did this derivative the longer way, right? And we got this as the answer. Here's an extra tidbit for you. The second derivative, remember we can do multiple derivatives. That just means that I would take a derivative of this thing that I just found as the derivative. So the derivative of the derivative being the second derivative. I would then take the derivative of this. Okay? So I'll box this in as one of my answers here. But notice right here, I bring the 2 down. That would be times 2x minus 0. Derivative of a constant is 0. So I get 6x. Also, one of the things that we found last time, right? 6x is the second derivative of this function. Okay? So as you can see, those first few basic rules that I've given you make a lot of our derivatives just quick. Especially when they're singular pieces like that or simple multiple pieces like that. Okay? So as you can tell, we're going to be taking derivatives of things that are way more complex. But this is where we're going to start, right? Make sure you can understand the basic power rule and then the fact that I can split up addition and subtraction. Okay, here's a next step up one. We've done this a little bit before already. Find the equation of a tangent line, right? We know how to do that. That's point slope form. I just need to fill in my point slope form, y minus y1 equals mx minus x1, or you could use y naught and x naught if you want. It doesn't really matter, as long as you're putting numbers for x1 and y1 or whatever, and you're finding a slope. Remember, if we're doing a tangent line, our slope is the derivative at the point we're interested in, right? So this slope right here, m, is going to be equal to g prime of negative 2, not g prime of x, although we have to find g prime of x first. Our rules work on functions, and then once we're in a derivative function, we can plug in values to that as well. Okay? Now, my x1 here, we already know, right? We already know this one. It was given to us, negative 2. How do I get y1 here? Well, if I know an x value, how do I find a y value? We plug it into the original function. That's just going to be g of negative 2. Right? Okay, so I have several different things going on here. I already know the x value. I need to find my slope using the derivative and plugging in the x value. I also need to know the y value that goes with the point of tangency, right? I'll do that by plugging the negative 2 into the function. First, let's find our derivative. In its current form, I don't have a rule for it. Remember, I warned you on this one. This is a multiplication of two functions. We don't have our product rule yet, okay? So I don't have a way to directly address the function as it is. However, it's not terribly complicated to multiply out. If it was several pieces and it was really complicated to multiply out, then I would say let's wait for that better rule that we have in next section called the product rule. But this one, it's not terribly bad. I can just multiply this out, and then each of the pieces will be ready to go with the rules I have now. So let's do that. My g of x is going to be 2x cubed. Then I'll have minus x and plus 8x squared. So 8x squared minus x, right? Minus 4. Okay, so let's see if you can employ the rules that we've talked about here now, right? Everything is added, and we just have multiplications of numbers themselves. That's okay. So here comes the derivative. G prime is going to be 6x squared. Notice I dropped the 3, right? The 2 was along for the ride, so basically 3 times 2 gave me 6. And then 3 minus 1 is 2. Plus, bring the 2 down, 2 times 8 is 16. And then 2 minus 1 is 1. Derivative of a linear piece is the coefficient, in this case negative 1 minus 1. Derivative of a constant is 0, plus 0 doesn't do anything for me. Okay? So now I just have to do a little bit of plugging. Right here I need to figure out my y value by doing g of negative 2, right? I can plug it into either one of these. Probably be easier to plug it into that one. And then I've also got g prime of negative 2 because I've got my derivative function right here that I can plug it into and get my slope. Okay? So now let's do that. G of negative 2 is going to be 2 times 8 minus 1, 7 is 14. Double check me real quick. 4 plus negative 2 is 2. Negative 2 squared is 4. Times 2 is 8. Minus 1 is 7. Okay, good. G prime of negative 2, I'm going to have 24 minus 32 minus 1. Right? So I've got, let's see, 6 plus 2 is 8. So negative 9 total. right? Negative 9. All right, so now I've got my x value, I've got my y value, and I've got my slope value. I'm just going to create my equation. I have y minus 14 is equal to negative 9 times x plus 2, because it's minus negative 2, right? All right, so that's y minus 14 equals negative 9x minus 18. Add 14 to both sides, and the result is y equals negative 9x minus 4. Okay? All right. So I hope this has helped you get used to the very beginning and basic laws that we have for derivatives. Stay tuned. The next one's on product rule and quotient rule. Very important structural rules. All right, guys, I just wanted to show you the graph of what we just calculated real quick so that you can see what was going on the graphical side. Here's that function x plus 4 times 2x squared minus 1. Right? Here it is in green right here. And what I'm going to do is I'm going to shrink the y-axis a little bit here and expand the x-axis a little bit. And yeah, they'll be out of sync a little bit. That's okay. I just want you to be able to see the points of what's going on here. Okay, and then let's create a point on the function negative 214, right? That's the point that we asked for the tangent line. We said we wanted to do the tangent line at the point where x equals negative 2, and that is the actual point on the function negative 214. Okay, and as you can see, I've typed in the equation that we calculated, and right here you can see it's completely tangent. It melds into the function there to the point where you can't tell the difference between them once it's inside of a certain neighborhood there, right? If I look at a small neighborhood of that function right there, you can tell that it's inseparable from it at that one point.